Assalamualaikum and hi everyone. Now you are watching 1.1 reaction rate video 4. In our previous video, we already discussed about reaction rate, graph concentration versus time, differential rate equation, and rate law. In this video, we will learn in detail about order of reaction and half-life. Since we have learned three different order of reaction, which is zero order reaction, first order reaction, and second order reaction, now we will discuss on how does the different order of reaction affects rate of reaction. For reaction A produce B, the general rate equation is rate is equal to K times concentration of A power of X. For a certain reaction with X is equal to 0, the rate law for the reaction is rate is equal to K times concentration of A to the power of 0. Since A to the power of 0 is equal to 1, so rate is equal to K. From the rate law, we can see that the rate of reaction is always constant. Therefore, this reaction is zero order with respect to A. For a certain reaction where X is equal to 1, the rate law for the reaction is rate is equal to K times concentration of A power of 1. Assume that initially concentration of A is 1.0 molar. So rate 1 is equal to K times 1.0 molar. If we double the concentration of A from 1.0 molar to 2.0 molar, so rate 2 is equal to K times 2.0 molar, or we can write as rate 2 is equal to 2K times 1.0 molar. K times 1.0 molar is same as here, which is rate 1. Hence, rate 2 is equal to 2 times rate 1. Thus, doubling the concentration of A will double the rate of reaction. Therefore, this reaction is first order with respect to A. For a certain reaction with X is equal to 2, the rate law for the reaction is rate is equal to K times concentration of A power of 2. Assume that initially concentration of A is 1.0 molar. So, rate 1 is equal to K times 1.0 molar to the power of 2. If we double the concentration of A from 1.0 molar to 2.0 molar, so rate 2 is equal to K times 2.0 molar power of 2. Or we can write as rate 2 is equal to 4K times 1.0 molar. K times 1.0 molar is same as here, which is rate 1. Hence, rate 2 is equal to 4 times rate 1. Thus, doubling the concentration, the rate will increase by a factor of 4. Therefore, this reaction is second order with respect to A. Example 1. Consider the following data for the reaction shown. Determine the order of reaction and write the rate law for this reaction. Solution. Look at the data given. In experiment 1, the initial concentration is 3.0 times 10 power of negative 3 molar. In experiment 2, the initial concentration is 9.0 times 10 power of negative 3 molar. That means from experiment 1 to experiment 2, we triple the concentration. What happened to the initial rate when we triple the concentration? Experiment 1, the initial rate is 9.0 times 10 power of negative 7. In experiment 2, the initial rate is 2.7 times 10 power of negative 6. That means the initial rate also become triple. So we can say that when we triple the concentration of N2O5, the rate also triples. So X or order of reaction is equal to 1. That means this is first order reaction. So the rate law or the rate equation is rate equal to K times concentration of N2O5 to the power of 1. Example 2. Consider the following data for the reaction shown. Determine the order of reaction and write the rate law for this reaction. Solution. This is the general rate law for our reaction. X is the order of fraction with respect to F2. Y is the order of fraction with respect to ClO2. Look at the data given. In experiment 1, the concentration of F2 is 0.10. In experiment 3, concentration of 2 is 0.20. That means we double the concentration of F2. So what happened to the initial rate? In experiment 1, the initial rate is 1.2 times 10 power of negative 3. In experiment 3 is 2.4 times 10 power of negative 3. That means the rate is also double. So we can say that when we double the concentration of F2 with concentration of ClO2 constant, the rate become double. So X is equal to 1. Next, look at the concentration of ClO2. In experiment 1, the concentration of ClO2 is 0.010. In experiment 2 is 0.040. That means we increase the concentration by 4 times, or we can say as quadruple. What happened to the initial rate? In experiment 1, the initial rate is 1.2 times 10 power of negative 3. In experiment 2 is 4.8 times 10 power of negative 3. That means the rate also increased by 4 times. So we can say that if we quadruple the concentration of ClO2 with concentration of F2 constant, the rate also quadruple. So Y is equal to 1. So the rate law is rate is equal to K times concentration of F2 power of 1 times concentration of ClO2 power of 1. Example 3. Determine the rate law and calculate the rate constant for the following reaction from the following data. This is the general rate law for our reaction. Based on the data given in the question, we can see that if we double the concentration of I minus, the rate also double. You can refer to experiment 1 and experiment 2. So, we can say that the value of Y is 1. That means the order of reaction with respect to I minus is first order reaction. Next, if we double the concentration of S2O82 minus, the rate also double. You can refer to experiment 2 and experiment 3. Therefore, the value of X is 1. That means the order of reaction with respect to S2O82 minus is first order reaction. So, the rate law is rate is equal to K times concentration of S2O82 minus power of 1 times concentration of I minus also power of 1. Next is calculate the rate constant. From the rate law, we can rearrange to become K is equal to rate over concentration S2O82 minus times concentration I minus. To calculate the rate constant, we can choose data from any experiment to be substituted in this formula. You can choose experiment 1 or experiment 2 or experiment 3. I choose experiment 1. So substitute all the values in this formula like this. Then you can calculate the rate constant and the value is 0.08. The unit is per molar per second. Next, we will learn about rate law graph. For example, we have A produce product. To learn about rate law graph, we need to look at the rate law or rate equation. This is rate law for zero order, first order, and second order reaction. This is the rate law graph for zero order, rate law graph for first order, and rate law graph for second order. As you can see here, all graphs have the same axis, which is rate versus concentration. This is because if we put y is equal to mx for each of the rate law here, we can see all the y-axis is rate. So that's why the y-axis here is rate. And all the x is concentration of A. That's why we can see here, x-axis is always concentration. The only difference for rate law graph is the curve of the graph. If we can see here, zero order, the curve is straight line and constant. Because zero order, the rate is always constant even though we change the concentration of A. For first order reaction, the graph is linear. This is because if we double the concentration of A, the rate will also double. For second order, the graph is quadratic because if we double the concentration of A, the rate becomes quadruple. The next term that you need to understand in reaction kinetics is half-life, or the symbol is T-half. Half-life is the time taken for the initial amount of a reactant to decrease to half of its original value. For example, we have initial concentration of A is 5 molar. Half of its original value means initial concentration divided by 2. So 5 molar divided by 2 is 2.5 molar. So the first half-life is the time taken from 5 molar to become 2.5 molar. Second half-life is the time taken for 2.5 molar to decrease to half of its value. So 2.5 molar divided by 2 is 1.25 molar. So the time taken for 2.5 molar to become 1.25 molar is considered as second half-life. The unit for half-life can be second, minute, hour, day, week, month, or year. Second example, if we have the initial mass of A is 50 gram, the first half-life is the time taken for 50 gram to decrease to 25 gram. The second half-life is the time taken for 25 gram to decrease to 12.5 gram. Thank you for watching.